This video covers hybridization.
When we went through Lewis structures, okay, there are some issues. Drawing the Lewis structures in and of themselves oftentimes don't match up with what the bond angles actually are. And sometimes the Lewis structures that we draw don't really show the way that the molecules actually behave. So we're going to have to alter some stuff around just a little bit. And we're going to talk about what's called the valence bond theory and covalent bonds. So when we look at bonds, okay, bonds are formed by sharing pairs of electrons, and they share pairs of electrons between atoms when the atoms overlap their orbitals. So as an example, if we were to look at a 1s orbital here, let's say we were looking at hydrogen, and a 1s orbital here, those two orbitals would overlap, and the two atoms would share pairs of electrons between those overlapping energy levels. The strength of that bond is dependent on the extent of the overlap. And the extent of the overlap is dependent on the orientation of the orbitals. So the greater the overlap, the stronger the bond is going to be. And that's when they're directly lined up with each other. So as an example, if we were to look here, okay, we have, this is a p orbital here, or depiction of it anyway, and this is a p orbital here, and they're overlapping their orbitals. Different than if they were at angles and they overlap their orbitals. Okay, there's a lot more overlap here when they're lined up directly in line with each other than when they're off center from each other. So that leads us to two different types of bonds. They're called sigma bonds. That's what this symbol is here. And pi bonds, which is what this symbol is here. So when we talk about sigma bonds form when the orbitals overlap essentially head on. So if we have two s orbitals and they overlap head on, or an s orbital and a p orbital and they're overlapping head on, or two p orbitals that are overlapping head on. Those would be what we call sigma bonds. Pi bonds are bonds that form when the orbitals are side by side. So as an example, this is a p orbital and this is a p orbital, and they're overlapping side by side, as opposed to up here when they were overlapping kind of head on. Okay, we're going to have less overlap here than we are here. And if we have d orbitals that overlap, again, this would be our d orbital here, and this would be our d orbital here. And because they are side by side instead of head on, it's an example of what's called a pi bond. Now, every bond, whether it's a single bond, a double bond, or a triple bond, every bond has a sigma bond in it. Single bonds only have a sigma bond because there's only one bond in a single bond. But double bonds and triple bonds have both sigma and pi bonds. So if we were to look at the covalent bond between hydrogen and chlorine, okay, it is just a single bond. This would be a sigma bond. There are no pi bonds in a single bond. If we look here, we have two oxygen atoms that are held together by a double bond. One of these bonds is a sigma bond. The other bond is a pi bond. And we're going to look at how they form in a second. Okay, if we were to look at two nitrogen atoms, they have a triple bond between them. Well, the triple bond contains one pi bond and one sigma bond and two pi bonds. So every bond, single, double, triple, every bond has a sigma bond in it. A double bond has a pi bond, and a triple bond has 2 pi bonds in it. So let's look at these as examples, and let's just put them in the chat real quick. Okay, we have 3 examples of bonds. Are they sigma bonds or are they pi bonds based on the way they're oriented? Then you kind of want to look at them, and are they head on or are they side by side? Okay. I think I can do that. Agreed. A is a pi bond. Good. What do we think about B? Agreed. B is a sigma bond. Okay, we've got 2 p orbitals head on. We have 2 p orbitals side by side. Okay, what do we think on C? A sigma bond again. Good. Okay. All right, so here's another kind of question we could get. Okay, here's a molecule. And we want to figure out how many total sigma bonds there are and how many total pi bonds there are. Keeping in mind that every bond contains a sigma bond, and double and triple bonds have either 1 or 2 pi bonds. Okay, so how many sigma bonds and how many pi bonds in that structure? All right, good. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 total bonds in our structure. That means there are 9 sigma bonds. This has a pi bond here, and this has a pi bond here, so there are 2 pi bonds. I agree. Excellent. All right, so let's look at another one. How many sigma bonds and how many pi bonds? A little more complicated, so a little harder to kind of keep track of. But again, every bond has a sigma bond, so just count up how many bonds are there. And then double bonds have 1 pi bond, and triple bonds have 2 pi bonds. Good, so let's take a look. It's hard to keep track here, but I'm just going to go right around. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bonds. So that means there's 16 sigma bonds. There's a pi bond here, there's a pi bond here, there's a pi bond here, and there's a pi bond here. Good, so 4 pi bonds. Excellent. All right, so now this is where we're going to go through kind of quickly, and then I'm just going to boil it down to what you need to know. So when we look at orbitals, oftentimes they become what are called hybrid atomic orbitals. So let's say we were to look at this molecule. This is actually water. Okay, so we've got oxygen here and 2 hydrogens here. Okay, we know that oxygen is 1s2, 2s2, 2p4. Okay, so we'd have 2 electrons here, 2 electrons here, and 4 electrons here. So we would involve s and p orbitals. Okay, and we would kind of expect the shape of our molecule to look something like this. Okay, but that's not really what that molecule looks like. And if we were to look at carbon, okay, this is CH4 or methane. If we were to look at carbon in that structure, it's 1s2, 2s2, 2p2. So we'd have 2 electrons here, 2 electrons here, and 2 electrons here. We would kind of expect to have something looking like this, and that's not what that molecule looks like either. So what we're going to do is we're going to talk about how the orbitals kind of rearrange themselves and become hybrids so that the pictures we draw on paper match a little bit more what the actual geometries are in nature. So we're going to talk about what are called hybridization of orbitals. Okay, and it has to do with wave functions describing isolated atoms. When they're in molecules, they're going to have new ways that they're distributed. And we're going to deal with what's called the linear combination of atomic orbitals. Okay, now there are 5 different combinations of linear combination of atomic orbitals. We've got what are called sp, sp2, sp3, sp³d, sp³d2. Okay, so kind of just hold on for a couple minutes. Let me go through just a couple things real briefly, and then I'll boil it down to what you need to know. Oh, somehow that got screwed up, and I don't know how. We're going to go faster. All right, let's just look at this. So this is an s orbital, and this is a p orbital. They look different, and in a molecule, they would give different geometries. But if the one s orbital and the one p orbital kind of mix together and meld together to make what are called hybrid orbitals, we've got one orbital here, one orbital here. We're going to still end up with 2 orbitals, but these orbitals are going to kind of be an amalgam of the original s and p orbital. So this is called an sp hybridized orbital, and this is called an sp hybridized orbital. Now, we started with 2 orbitals. We ended up with 2 orbitals, but the thing that happened is now these 2 orbitals are exactly the same, whereas before the hybridization, they were not. And if we wanted to look at, let's say, beryllium as an example, okay, beryllium has 2 electrons in its 2s orbital. This is unhybridized, but it could become hybridized to make 2 sp hybridized orbitals, each with 1 electron in them. That would leave 2 p orbitals unhybridized. So, well, why would it do that? Because then these 2 hybridized orbitals are equal, and that's what leads to this linear arrangement we would see with molecules that contain beryllium as their central atom. Now, if we were to look at sp2 hybridization, it has 1 s orbital and 2 p orbitals that kind of meld together. So we've got our 1 s orbital and our 2 p orbitals. There's a total of 1, 2, 3 orbitals to begin with. And what these orbitals kind of do is they meld together and they kind of become somewhere in between an s and a p orbital. And we end up with 3 sp2 hybridized orbitals. Okay, we had 3 orbitals to begin with. We have 3 orbitals after this hybridization. The difference is now all of these orbitals are exactly the same. And what that leads to is a trigonal planar arrangement that we would see in something like boron as our central atom. So we have our 2s electrons and our 1 2p electron. Okay, they are going to be found in 3 hybridized orbitals. So this is somewhere in between an s and a p orbital, and this is somewhere in between an s and a p orbital, and this is somewhere in between an s and a p orbital. And then we have 1 p orbital that wasn't part of the hybridization. Now, if we have sp3 hybridization, that's going to involve 1s and 3 p orbitals that become hybrids. So we have our s orbital and our 3 p orbitals. There's 1, 2, 3, 4 unhybridized orbitals to begin with. and they kind of meld together, we're going to end up with 1, 2, 3, 4 orbitals. We're not changing the number of orbitals when we go through this hybridization process, but we're changing the shape of those orbitals. Now, these are all equivalent orbitals, and they're referred to as sp3 hybridized orbitals. Now think about this. There's 1s and 3p. 1 plus 3 gives us 4 orbitals. So anytime we need 4 things coming off the central atom, 4 effective pairs coming off the central atom, we're going to need sp3 hybridization. So let's say we wanted to look at water. Okay, so this would be our Lewis structure for water. And we're going to look at the hybridization on our oxygen. Well, wow, I don't know how this all got messed up a little bit. If we look at oxygen, we have 2 bonds and 2 lone pairs of electrons. So on oxygen, we're going to need 1, 2, 3, 4 equal equivalent orbitals. So those orbitals are each going to be called sp3 hybridized orbitals. So here's our oxygen in the middle. Here's 1 sp3 hybridized orbital. Here's the second sp3 hybridized orbital. Here's the third sp3 hybridized orbital. And here's the fourth sp3 hybridized orbital. Okay, they're all exactly the same shape. And then we've got our hydrogen that comes in along here, and we're going to form a sigma bond here when they overlap head-on. And we've got a hydrogen bond here that's going to form a sigma bond when they orient themselves head-on and overlap. And then we'd have a lone pair of electrons in this hybridized orbital and a lone pair of electrons in this hybridized orbital. That would give us an electron geometry that's tetrahedral. And it would give us a molecular geometry that's bent. If we didn't make hybridized orbitals, that's not what we would see. So let's say we look at ethane. Okay, ethane has the formula C2H6. Okay, or we could write it as we've got a carbon here that has 3 hydrogens coming off of it. And then we have a carbon here that has 3 hydrogens coming off of it. So maybe it looks something like this. Okay, here's a carbon and there's 3 hydrogens coming off. Okay, here's a bond. Here's our second carbon and we've got 3 hydrogens coming off of it. Well, if we wanted to talk about the hybridization for this molecule, okay, let's look at this carbon here first. Okay, that's what this would represent here. Well, there's 1, 2, 3, 4 things coming off of this carbon atom. We want a hybridization that's going to give us 4 equivalent orbitals. So sp3 gives us 4 equivalent orbitals. So this is an sp3 hybridized orbital. This is an sp3 hybridized orbital. This is an sp3 hybridized orbital. And this is an sp3 hybridized orbital. The same thing would happen with the second carbon. Okay, it would have 4 sp3 hybridized orbitals. And then the hydrogen would come in and overlap here, and the hydrogen would come in and overlap here, and the hydrogen would come in and overlap here, and here, and here, and here, and we'd form sigma bonds here, 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 and here. But in order for us to have a tetrahedral arrangement around this carbon would have to be sp3 hybridized. And in order to have a tetrahedral arrangement around this carbon, again, it would have to be sp3 hybridized. Now, sp3d and sp3 or D2 are for hypervalent electron configurations or Lewis dot structures. So one sulfur, or one s orbital, three p orbitals, and one d orbital would make an sp³d hybridized orbital. And there would be 1 plus 3 plus 1. There would be 5 equivalent sp³d hybridized orbitals. We would need this kind of hybridization if there are 5 things coming off the central atom. Okay, if we had 6 things coming off the central atom, we would need sp³d2 hybridization. 1 s orbital, 3 p orbitals, and 2 d orbitals becoming hybridized so that we end up with 6 sp³d2 hybridized orbitals. So if we were to look at this structure here, we've got 1, 2, 3, 4, 5 things coming off the central atom. Each of the orbitals have to be equivalent or the same. So we would have 5 sp³d hybridized orbitals to give us this trigonal bipyramidal shape. And if we had 6 things coming off the central atom, we would need 6 equivalent orbitals. sp³d2 hybridization would give us 6 orbitals that are all the same. Each of these orbitals would be an sp³d2 hybridized orbital. So this summarizes up what you essentially need to know, okay? If this is our central atom here, and there are 2 things coming off the central atom, the hybridization is going to be sp. 1s, 1p, that's going to give us 2 hybridized orbitals. If we have 3 things around the central atom, the hybridization is going to be sp2. Again, there's 1s and 2p, that's 3. Anytime you have 3 things coming off the central atom, the hybridization is going to be sp2. If we have 4 things coming off of the central atom, the hybridization is going to be sp3. Again, there's 1s and 3 p's. That's where we're coming up with the 4 from. If we have 5 things coming off the central atom, the hybridization is sp3d. And if we have 6 things coming off the central atom, the hybridization would be sp3d2. So essentially what you would have to do is draw the Lewis structure, okay? Decide which one it is, figure out how many things are coming off the central atom. And by things, I mean either atoms or lone pairs of electrons. And dependent on how many things are coming off the central atom will determine what the hybridization is. Now, let's say we're looking at this, okay? We want to figure out what the hybridization is. And we want to figure out how many sigma and pi bonds there are. Okay, so I'm going to do just one of them for you. And it's not going to be for the hydrogens because they don't become hybridized. But we'll look at nitrogen just to give you an idea. Okay, first of all, nitrogen has 1, 2, 3 bonding pairs and 1 lone pair. So nitrogen has 4 things coming off of it. So the hybridization has to have 4 equivalent orbitals. That would be sp3. Okay, that would be the hybridization. If we were to look at this carbon, it has 1, 2, 3 things coming off of it. This counts as 1 thing. It's 1 bond. Okay, it's a double bond, but it's 1 double bond. So carbon would need to have 3 equivalent orbitals or hybridized orbitals. So this carbon would be sp2 hybridized. Okay, so go around through here, figure out what the hybridization would be on each of the atoms. Again, not on the hydrogens because they don't become hybridized. They only have an s orbital. And then how many sigma bonds and how many pi bonds are there?
So the lone pair electrons, remind me again if they, what kind of bond they act as.
They don't act as a bond. So this lone pair is not a bond, but there has to be an orbital on this nitrogen that contains this double or this lone pair of electrons. So
okay.
Let's look over here. Let's look at this oxygen. Okay. This oxygen has 1, 2, 3 things coming off it. It has a bond and it has 2 lone pairs of electrons. So this oxygen has to have 3 hybridized orbitals. Okay, 3 equivalent orbitals. So sp², 1s and 2p. So sp² would give you 3 hybridized orbitals that are all equal to each other. So this would be sp² hybridized. Does that help?
Yeah, no, I'm just looking at this and like the sirens are going off in my head, being like, oh my gosh, oh my gosh, oh my gosh.
That's okay. We'll go a little at a time.
So if anyone wants to study this weekend, please. This is scaring me.
Oh, it shouldn't.
You're not the only one.
I will tell you that, and I've said this before, on Canvas, I did put like supplemental videos, and they are hopefully helpful. They do have some animation in there that might be a little bit helpful too. So you have that as well. So actually, even though the answers are on the next slide, we'll just do them together, okay? So we did this one already. We did this one, right? Let's look at this carbon. Okay, in the chat, how many things are coming off this carbon? 3, right? 1, 2, 3. Okay, what would our hybridization be? I know you can't put a superscript, that's okay. What would give you 3 of the same orbital, 3 equivalent orbitals? sp², agreed. 1s, 2p, so just say 1 plus 2 equals 3. That's all you have to do. If we look at this carbon, okay, how many things are coming off of this carbon? 4. 1, 2, 3, 4. Okay, what would the hybridization be? Just add up the superscripts. sp3, agreed, okay? If we look at this nitrogen, how many things are coming off this nitrogen? 4, right. There's 3 bonds and there's a lone pair. So that lone pair counts. So 1, 2, 3, 4. We need 4 equivalent orbitals. So what would the hybridization be? sp3, agreed. Let's look at this carbon. Okay, how many things are coming off this carbon? 3, right? 1, 2, 3. What would the hybridization be? sp2, good. Does that help a little bit? Hopefully. All right, so sigma bonds, we just count them up, right? So just count all the way around. Every bond has a sigma bond. So there are 30 bonds in here, okay? We have a pi bond here. 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 So there are 5 pi bonds. Good. So boiling it all down, okay? Look at the atom of interest. How many things are coming off of it? And by things, I mean bonds and lone pairs. How many things are coming off of them? And I'm going to boil it down to the simplest thing. The superscripts in the hybridization have to add up to the number of things that come off the central atom. Okay? Now, why do we need to know that? Well, it kind of helps us to explain where double and triple bonds come from. So if we were to look at this structure here, okay, it has 3 effective pairs. Sure. So that means we need to have what kind of hybridization on this carbon? What kind of hybridization is on this carbon since there are 3 things coming off it? sp2, okay? What kind of hybridization is coming off of this carbon since there's 3 things coming off of it? sp2. So out of the 3 p orbitals, 2 of them are involved in the hybridization. 1 of them is not, okay? So when we look, okay, we're gonna have 3 sp2 hybridized orbitals, one for here, one for here, and one for here. And the same thing over here, one hybridized orbital for here, one hybridized orbital for here, one hybridized orbital for here. But there's this unhybridized orbital that's left over. And that unhybridized orbital is what's going to cause our pi bond. So the hybridized orbitals all overlap, which is what we saw in the examples that only had sigma bonds in them. But we have an unhybridized p orbital here and an unhybridized p orbital here. They overlap kind of above and below the plane of the sigma bond, and they form a pi bond. This is one bond. So we have a sigma bond here, and we have a pi bond here, and that's what gives us a double bond. Now, let's say we were to look at this structure here. What's the hybridization on carbon? It's the same on both of them. For this carbon and this carbon, what would the hybridization be? Put it in the chat. What would the hybridization be? sp, right, because I've got one, two things coming off of each carbon. So this is sp hybridized. That means one of the p orbitals is involved in the hybridization and two p orbitals are not. So if we wanted to look at the hybridization again, the s and two of the p orbitals are going to be involved in the hybridization, but we're going to have two p orbitals that are left over. This is wrong. This should say sp, not sp2. This is wrong. This should say sp, not sp2. Okay, sorry about that. So this is an sp hybridized orbital. This is an sp hybridized orbital. And there are two unhybridized p orbitals. Okay, so we've got our hybridized orbital here. Again, notice it says sp, not sp2. This is wrong. There are two unhybridized p orbitals. So the hybridized orbitals form our sigma bonds. This is one of the unhybridized p orbitals. This is the other unhybridized p orbital on this carbon. And the same thing on this carbon. There's an unhybridized p orbital and unhybridized p orbital. The unhybridized p orbitals, one of them forms a pi bond and the other one forms a pi bond. So we end up with a sigma bond with the hybridized orbitals and two pi bonds with the unhybridized orbitals. No, we're not going to do that. Okay, so again, the kind of trick in a way for hybridization is count how many things are coming off the atom, and that's how many things have to be in your hybrid orbitals. Anything that's unhybridized would then form a pi bond instead of a sigma bond. Okay, and again, I know it's a lot of stuff. I do have a couple of videos on Canvas, which maybe will be helpful. They have a little bit of three-dimensional stuff to them, and maybe that will help out a little.